Well, thanks a lot for everyone showing up. So yeah, I love doing these talks. I think the first one was like 6 here or something like that, 7, I can't remember. It's been a long time. I do them like every year and they keep having me back, so apparently I'm doing something right. So our presentation today is hardware hacking Ginsu chef style. So what the hell does that mean? So this was kind of a long, drawn-out process where I had to learn a lot of different things I hadn't done before. So I just want to be able to share that with you. So generally, in this particular talk, I had a device. I'm the research lead for IoT technology at Rapid7, so I get to like tear stuff up all the time. It's kind of fun. So I had a device I was doing some assessments on, and I have the device here, and I'm not even going to give you the product name because actually the product's pretty good from a security standpoint. Their whole product ecosystem was fairly solid. But you know, it had a UART console on it, and I wanted to get root access, and it prompted me for a password, and I couldn't get the password. So that's when the journey went. It was like, okay, I want to gain root access to this so we can do some other testing of the device and look at the firmware and do some in-memory type testing, which I haven't done yet, but I finally got root access on the device. So I want to walk you through kind of the process that I did here. And this took a long time, so it was done in pieces. You know, I go off on other projects and come back. And I hit a certain roadblocks and go, okay, there's something new that I got to learn, so let's take the time to learn it. Then there's some stuff where I need some new equipment, so it takes me a little time to get the equipment. And then spend time talking to other professionals that have done some of this stuff and learning some of the nuances about it and kind of move on from there to the point where we finally got root level access. Now this talk would be absolutely perfect if I could actually do the whole process here, but it also involves some solder type stuff, which is kind of hard to do on stage, and it makes it fairly difficult, and no one wants to stand there and just watch something solder melt. You know, it's kind of boring as hell. So I come up with this talk called Hardware Hacking Ginsu Chef Style. So I don't know how many people are familiar with the old commercials on Ginsu knives. Everyone remember that? Those are pretty freaking cool. So I'm like, okay, so that's kind of, this is the whole slice and dice of the hardware to get root access on the device. But you really can't do all that unless I have a freaking Ginsu Chef knife. So of course I went out and bought one, and they're still available. So then it was like, well, how can I do this? So I thought about bringing it, but you know, freaking TSA gets all pissed off when you bring like this 12-inch knife on board the plane. So I couldn't do that. So I thought, well, what can I do with a Ginsu Chef knife? So I decided to, you know, let's see if we can recreate some of the freaking commercial. But let's do it IoT style, okay? So let's see if we can get this going here. So my wife filmed this for me, and of course everyone's aware that she really tolerates the stupid shit that I do. So here we go. So let's cut this damn Amazon Echo in half, and as you're gonna see real quick, the Amazon Echo is a pretty damn tough piece of appliance. So, still sharp as ever, man. Now, I actually opened it up, and all the circuit boards were still in there, but I stripped the metal core out of this because it's a heavyweight metal core, and I'm thinking if I do get through the case, I'm never going to get through that big chunk of steel. But of course, Ginsu 0, Amazon Echo 1. So let's go ahead and get started. So in this particular case, one of the first parts of the whole process, what the hell is that saying on there? Start the slides from, whatever the hell. So you get that on there, it'll go away. So the first part of any assessment is kind of that examination. So it's literally, you know, it's open it up, let's start thinking about the device, let's start looking at it. Let's see how all the pieces and parts work before we go to the next step. So in the examination, we kind of look at the circuit board and go, okay, what's interesting on these circuit boards that we could possibly get usable data from? And this really cool, this particular chip right here is an embedded multimedia controller chip. So how many people have cell phones? I expect everyone has cell phones. Every one of the cell phones, the memory storage on those is embedded multimedia controllers. That's what exists on those. So it can typically be fairly large size storage. Usually starts out about 2 gig in size, which is the size of this chip, and go up to like 64 gig is the normal range of the chips you see in embedded multimedia controllers. And then there's another one known as an embedded multi-chip package, which contains the embedded multimedia controller and RAM in it also. In this case, it's just the embedded multimedia controller. The one chip, let me see if we can get to it. This chip right here happens to be the RAM. So they decided to do it in separate packages, and there's a number of interesting pieces in here on this device as you look at it. We also have a header here. This dish initially didn't have any pins on it. I had to actually solder the pins onto the device. And there's, I think there's another header over here. So this was the first one I examined, and we determined that it had UART, Universal Asynchronous Receive Transmit, the ability to get a console on the device. So at that point, you fire the device up. So let's do that. So we actually have one plugged in here. I'm hooked up to it. I'm hooked up to it with a Shikra. I don't know how many people are familiar with Shikra devices. We could actually show you one here in a little bit. But let's go ahead and power it up. It should be ready to go. And we can watch the device boot up. This one boots up fairly quick, which is kind of nice for presentation purposes. But it prompts you for a username and password. So in this case, you know, you can guess away. You're probably not going to guess access to the thing. So the next level is let's pull the firmware off the device. Load the agent. Let's pull the firmware off the device and see what we can get from there. That's generally the direction you want to go. So you have to excuse me jumping back and forth between slides. So we talked about the embedded multimedia controller. This one happens to be a Micron chip. In this particular case, 2 gig as I mentioned. And the IDs was JW999 on the chip. And there's another number above that, 6R, whatever it was. So when I did my research trying to find the data sheets to initially figure out this chip and what it is and how it works, because I really wasn't positive it was a standard embedded multimedia controller initially. It looked like one, I thought it was. But let's find the data sheets before we start tearing shit apart on the device. So we weren't able to find that actual number, but we found a cross-reference. I can't remember where I found the cross-reference, a lot of searching. I found a cross-reference that pointed over to these MTFC embedded multimedia controllers. So now I know it's an embedded multimedia controller, and these chips are like freaking cool as shit. So typically when you're trying to pull memory off a device, you either have to pull it, put it in some kind of weird reader. You read the data off, it's a big freaking blob, and then you got to explode it out, use bin walk, try to tear the thing apart. Sometimes it works, sometimes it doesn't work. The cool thing with embedded multimedia controllers, they're the same kind of chips that exist in SD cards, as an example. So you can actually mount the chip up like a file system. We already talked about the UART, and we'll get to the chip a little further in a minute. But again, with the header, we booted it up, we got a root process, that's the actual Shikra up there. It's about a $45 device. It does JTAG, it does SPI, IC2, there's a couple other things it does. But I like using it for UART connectivity. It works pretty good for connecting up quickly for a UART on it. And I like to use CoolTerm as a terminal, but there's a million terminal programs out there you can use. Hook this up to your device, connect it to your serial terminal, and as you see, we're actually able to boot the device up and get a console, either a debug console or a console we can log in if we happen to have the passwords to the device. So the next phase is disassembly. So we have the device, we know we have an embedded multimedia controller, but now we want to get the information off the actual chip. So how are we going to do that? The way we're going to do that is we're going to take the device apart. Now these chips happen to be what's known as BGA chips, ball grid array chips. So there's no solder joints that are visible that you can take a soldering iron or some kind of chip quick desolder tools and desolder. You have to actually do some kind of heat reflow, either with hot air or infrared. The device on the left-hand side here happens to be an infrared device. I don't have one of those. They're kind of nice. Someone recommended that I buy one. It was like $700–800, which is like the cheaper end, and it goes up from there. And I'm like, It's a little more than I want it to spin. On the right-hand side is a hot air reflow. These work really well. They're typically inexpensive. You can buy these off Amazon for, I don't know, $80, $90. You can also, I'd recommend buying the stands like that are over there. They're sold separately. They're like anywhere from $30 to $40. This gives you a fairly decent rig for $110, $120, somewhere around there. Very doable. The one thing you want to remember about these, they're like cheap Chinese pieces of shit. So when it's not being used, you unplug it. That way it doesn't explode and burn your house down when you're not around. Because they have a really bad history of doing that, which is never good. The other option is a cheap Chinese oven. This was about $185. I love this. This is what I did not use this originally for disassembly, but I used it for assembly of the device. The ovens are really sweet. And we'll show an example of using how well the oven works for pulling a chip here in a second. I got a video of that. But our initial aspect was to go ahead and pull it with hot air. So I used the hot air, and you see the, I'll set the speaker off. You see the tape that's on there, and I never can remember the name of this tape. It's this thermal tape. It's this yellow tape. It's, Kapton, is that it? I always forget the name of it. That's one thing you'll find. I can't remember people's names, and I can't remember names of shit. So, but it works real good. You lay it out across the device, around the chip, so you can protect the other components on the chip. You're using hot air, it's going to melt the solder. If you get it hot enough, you can melt the solder components around it. And you're also blowing air, so it can blow components away, small capacitors, small resistors. So I typically lay this stuff out. I have it in from this width all the way up to like 2-inch wide that I can lay out. So it protects the components thermally around it, fairly decent. It'll hold up to some pretty good heat, and it prevents you from damaging the rest of the board, so it works really good. So we use the hot air, we get it hot enough. The melting temperature of solder is 183 degrees Celsius, and that's for the 6337 solder that are used on these. So you bring it up to that temperature there, close to it. You can buy cheap thermal probes if you want to put a thermal probe on there. I have one, I don't always use it. These boards dissipate tons of heat. So you know, I heard a lot of recommendations, I read a lot of stuff on doing this, and they say, well, set it at this temperature, when it comes up, it'll pull off. So I set it at that temperature, even used a temperature probe. It got to that temperature around it, and it's like, hell no, it didn't come off, didn't even budge, because the board was dissipating so much of the heat. So I found out is, bring this temperature up slowly, because you don't want to thermal shock the chip and damage it. So I usually bring it up, you know, up to 70, 100, and keep going up. And I take it up, this was a Fahrenheit measurement on my device. I cranked it to the full temperature of the device. Once I get it up to a safe temperature, I just keep going. And then I just let it cook, and I keep checking it. And as soon as it's loose, I pull it off there. And that way I don't overheat the chip and damage it. I've done this dozens of times, and it seems to work for me. The recommendations that I read via Google and various other things totally failed for me. Maybe it's me, I don't know. This worked for me, and it worked pretty good. So we got the chip off. At that point, we clean it, so how are we actually going to read the chip? Now, there's a number of chip readers available out there, and I'm actually going to pass some of these chip readers around. So I ask that so the tops of these chip readers open up. So we have these are kind of cool, that look like an SD card. So literally, you just open it up, you put the chip in there, you close it up. So I'm going to pass this around so you can take a look at it. So if you open it up, close it up, just do it kindly so we don't damage it, because they're pretty flimsy. And then this is a little more expensive one. This one hooks up USB 3, makes it hook up a lot faster. Same thing. And I'll pass these around so you can just take a look at it. So you get a chance to see these. These vary in price from about $80 to like $130 for the more expensive one. But there's resources online, and there was actually a presentation I think was done at Defcon last year or the year before that on how to build these yourself. So if you want to go the hacker route, there's options out there which may or may not be cheaper. I haven't looked at the price ranges of it. But these work pretty good, and they're $85. There's a series of 4 of them out there that cover the most common chips that you run into. There's the 153 ball BGAs, 169s, 221s, and I think it's a 526 or something like that for BGA. So there's a forum that'll cover most of the embedded multimedia controllers and the embedded multi-chip packages that you're actually going to encounter. But when we're dealing with IoT, mostly you're going to encounter either the 153 or the 221s. The 221 is a embedded multimedia chip package where both the RAM and the embedded controller stuff are all on the same chip. So those are the most common. When you get into more bigger devices like iPads and tablets and cell phones, you may see the other series of chips available. Oh, there it is. So we mentioned extraction. So the next thing is actually extracting the data. So I have one of these here with the actual chip that was pulled off the board. And if everything works right, come over here. And you take the device, you put the chip in it, you hook it up, and you hit the button. And you see the entire file system mount up. So all the partitions on the chip will mount straight up. On the chip, they are read-only, so you cannot alter them or modify them. But you have access to this. So literally, you can go in here, you can go to the shadow file, and you can pull the shadow file off the device and look at the password. We pulled the password off this one, which I didn't think was a complex password. I was convinced it was the old DES style, which is a serious weakness. And I gave it away to several people that I know that have these monster cracking machines. So I figured, hey, they're going to kick this back to me in 30 minutes. Several days went by, and I was told, no, our system finished through the entire 8-character possibilities that you potentially see with the DES, and it did not crack anything. So frustrated at that point is where I started on the second part of the journey. Okay, now how do I change the password on the device? How do I modify the code? So the best way to modify the code, let me check my slides, make sure I'm on the right path here. Current slide is modification. Okay, so we get into the modification of it. So I put some of this data in the slides, even though we're not actually using the slides, just so some of that will be available for people. So now that the chip's mounted up, how do you access the chip to actually pull the data out of it? So we find out the chip, everything mounts up, and we have all of these volumes. There's 8 volumes associated with this chip, or 8 partitions on the chip. This makes it well easier than if you pulled the entire blob off and had to try to separate it out. So the eMMC chips are seriously easy for extracting data. In this particular case, the partition 4 is actually an extended partition and contains these other 4 partitions. The interesting partitions in here are partition 3 and partition 6. Those are the actual Linux operating system on this device. And the reason why there's 2, there's a number of reasons based on the type of technology and how they're doing it. But generally, the way it works is anytime you do a firmware upgrade on a device, it has to overwrite the chip. So it's going to overwrite the non-functioning partition. There'll be 2 partitions. So it's overwrite the one that's not the primary, and then it's going to switch to primaries. So that will bring the device to the new active one when it reboots after it writes the data to the actual chip. So the way we actually do this is, let me just make sure I don't have anything in here. Oh yeah, we do. Gosh, dang, man. Let's get rid of that. So as we're going through this, don't hesitate to ask any questions. So DD. DD's, and I assume a number of you are familiar with DD. So we can actually do the actual device, SDB6, we're going to do that, and we're going to output it, we'll call it partition, like we had on the other one, bin, partition bin. So at this point, it should read the chip, shouldn't take too long, and pull that data off there into a file. So now we actually have the file off there. So we could actually look at this with binwalk real quick. And it's going to produce a whole bunch of crap on here, but Most of that is garbage. The main thing we're looking for is what is the file system. So we can see this happens to be a squash file system. So now we're actually able to identify the file system type so that we can actually alter it. The only way to alter it at this point is to unsquash it. So if we unsquash, learn how to spell squash, the file system, partition bin, it'll actually go through and separate it out. And now we have the entire file system exploded out on the device. So from here we can go in and potentially make alterations to the device, which is generally what we're going to do at this point. Now it's actually readable and editable. So it's easy enough to, when I did this hack, there's 3 files that I actually altered. The password file, the shadow file, and the actual group file, so that we have everything. Since we want a real password, we'll just go ahead and use, excuse my laziness. Let's see if that works. Of course it didn't. Yeah, here we go. So we can actually generate a hash for a password. You can see I'm actually used to. I wonder if that worked. No. Don't do that. Damn it. So then we can go ahead and change over to the directory. So we're in a squash file system, go to EDC, VI, the password file. And from here, we'll go ahead and we're just going ahead and we'll create another user in here. We'll change his name to Bubba. That's what I used on the other one. We know this runs up to a user of 1,000, so we'll go ahead and change that to 1,001. Change this one to 1,001. Save that out. And then we'll go ahead and VI shadow. Change the password here. And then we'll go ahead and change this to Bubba. So there's a reason why I changed the root password, just in case, and created another account. Obviously I want to get the root, but there was a chance, my fear was, and it turned out to be legitimate, that root couldn't log on from this terminal, and that happened to be the case. We'll try this again. There we go. So we go ahead and put the new password in, which is test12344. Write that out, and then we want to VI the group. So again, with group, we're going to go ahead and we're going to add Bubba under root. And then add Bubba as his own group, write that out. So once that's written out, the next thing to do is we want to be able to pack this back up. And again, we are going to cut and paste. Hell, we'll just type it in. We'll see how good I can type. Everyone check my spelling. We'll give it a new name. That's the altered one. Someone will have to look up all the different switches and settings for this. I had remembered, but I actually forgot how those were done. So we repacked this thing up into a squash file system. So now we have it packed up under partition alt bin. So at that point, we can actually rewrite it out. So again, we can write it right back to the actual chip. There it goes. That's writing it back out. So we can write it back out to the chip, and now we have an altered chip, which gives us, well, eventually it takes a minute to write the chip. Any questions while this is writing this out? Yes, sir.
Hang on a little bit. So one way file system is only read-only, but then I guess
yeah, when it's a squash file system is only read-only, okay, period. So even when you pull the partition off, it's that partition data, that binary is still, I mean, yeah, I guess you could go into the binary and alter it. But on the chip, it's read-only, period. All of those partitions will only be read-only. So the only way to alter them is remove them from the chip. Explode them out in some fashion where you can alter the data, whatever that be. Whether you want to do it through a hex editor or binary, I've done stuff like that before. Or in this case here, it's easy enough to do unsquash. Unsquash it out to a full file system. At that point you can go in and edit, change, add code, anything you want, backdoors, literally do anything you want to this device. Set up new executable code on startup, everything you want to do. And at that point, when you're done, you squash it back up into a standard squash file system and put it, and then from there, you or back into the binary, you re-squash it, and then burn it back to the chip, which is what we're doing, which is the actual what I did. And of course, the first time I did this, I'm thinking, there's like no way in hell this is gonna work, okay? And then in this whole process, you know, I still had to learn some other things. So now we have it all squashed up. Everything's packed up good. It's burned onto the chip. And there's one other thing I wanted to show. And we had, I mentioned this earlier. And I mentioned pulling the chip physically off the board with hot air. The easiest way to do it is with the oven. I love the oven. So with the oven, and of course you got to use either hot air or oven to do this. So it reaches into the oven and it brings it up to the 180. In this case, I brought it up to like 207 degrees. It brings the whole board up to that, or 207 degrees Celsius. It brings the whole board up to the hot enough temperature. You just reach in there and pluck the components off. The cool thing with this, and when I first started thinking about this, you know, if I heat up all the components on the board, what the hell is going to happen to all the other ones? Are the ones on the bottom going to fall off? Well, there's a cohesion factor with the lead solder that actually keeps all the components stuck to the board. So you can literally take a board when it's up to that temperature, and you can basically tap a chip and watch it wiggle, and then it'll line back up with the solder. So it's kind of cool, but you flick it too hard, it's gonna like hit the wall. Which I've done. I've done nearly that bad before. Just as a side story with doing this, I was doing an engagement where I had to pull the embedded multimedia controller off a Android-based device for some research. They wanted me to see if the code was properly encrypted and all that stuff. So the way to do it is with the oven. It turns out when we're looking at the board, all the embedded multimedia controller is actually epoxy to the chip or to the board. So I'm thinking, oh shit, and it's the kind of epoxy that flows up underneath the chip. So I literally ground all the epoxy around the whole chip off, got a real thin metal spudge, heated the whole board up, got some gloves so I didn't burn the shit out of myself, grabbed the whole of the board and popped the chip, and when the chip came off, it came off nice and easy, but in the jolt, I flung components all over the room. So I literally went around the room, the ones I could see and pick up, And I shipped it back to the owner, the manufacturer, in a plastic bag, and the whole bottom of the bag was like full of these microscopic caps and resistors and all this shit. It just went everywhere. So once you bring it up, you just got to be gentle with it. Be precise with the sucker to be able to pull those things off. I would recommend, so from suckers, you can go buy these, which are, and what I'm not going to make a recommendation for this, okay? So you have these little suckers here where you can press it in and it creates this vacuum. But it takes a lot of force to create that vacuum. Enough force when you're dealing with closely packed boards that jolt could do some stuff. I've actually messed a few things up with this. So I went out and bought an entire vacuum pump one. It has a hose to it. And then it's always sucking, then I always just tap the chip and I have it. But you may feel comfortable using one of these. I don't. I have it because I didn't have anything better to do with my $9. So the next step is reassembly. Now there's a couple components I was hoping to bring here that I thought was in my case, but it wasn't, and it was the reballing kit that's shown in the picture there. But so the next thing is I had to learn out how to reball these chips. How do we go and take these microscopic chips and put all these balls on the bottom of them and make them stick and then put it all back together again? So I'm really big on microscopes. If you want to get into this stuff, get yourself a microscope. This is like a really good one. You don't need one that big or that fancy. There's a cheap one out there that I consider cheap that's really good from AmpScope. It's about $185. So if you're really wanting to get into this, eventually I'd recommend doing that unless you happen to be like under 25 and have supervision and can actually see this stuff. I'm actually going to pass some of these components around, so hopefully I get my chip readers back. Those aren't cheap. But so there's a couple ways of doing this. There's a device, you can get this device here that you can put a screen over. And the screen has all the little holes punched in it. You put it on there, and then you just pour the balls in there and you line them up in the holes. The first thing you do is you take the chip, make sure it's clean. You put a fine layer of flux on it. Okay, fine, real fine. You take a scraper, it's almost like razor blade edge scraper. Well, not quite that good. I have one. I think it's a piece of shit, but I did have one. Oh yeah. So you have one of these, and you use that to put the flux on. But when you're dealing with stuff at such microscopic level, if you put that under the microscope, it's not like smooth and straight. So it's like another Chinese piece of shit. But you go ahead and you scrape all the solder off so it's a really thin layer. That's very important, it's very thin. Because if it's too thick, what will happen is, and I've made this mistake a couple times, the solder balls, when they're all on there and you put them in the oven to reflow this, will float up on top of the solder when it liquefies, and they'll like freaking merge together. So then when you get your chip, instead of having all this 153 little balls in there, you have like 120, and the rest of them are just big freaking globs, which doesn't work. So I've done it with the reballing kit where you use the screen. I don't like that. I'll tell you exactly the best way to reball these is by hand under a microscope. Put it under a microscope and you put the flux it out. You pour the balls on the edge of the chip like we did right here. So we're seeing right here. And you take a fine point tweezer and you roll each one of the balls onto the pads manually, all 153 of them. So I give you an idea of the size of this. You got to see this. I had it here. Here it is. Huge camera. So everyone can see that real good. Let me see if we get a light on here. So you can see the chips. Get an idea of the size of the chips on the penny. And those are 153 balls go on those. So we have two of them here. This one here is not been reballed. It's been clean. I reballed this one the other night before I got on a plane. So you can see how size they are. So you get it under a microscope, so it looks this big. It's a hell of a lot easier when it looks this big, okay? And then a lot of people are like scared of this. I remember the first time I saw this in a video, I'm like, holy shit, really? I couldn't do this. I'd have a nervous breakdown. It's not true. It's not that hard. And when it comes to stability, the way I found out it is often you shake. And a little bit of shake means when you go down there, you're like fling balls everywhere. That's about all you're going to accomplish. But I found out that when you get your elbow and arm stabilized, you take your left hand, put it on top of your hand, and put weight on it. When you put weight on your hand for any soldering, when you're shaking, it'll stabilize it. It'll make it real stable. And I can sit there and I can actually roll the balls on every one of these pads. And I usually do about a quarter of it and then take a couple minute break, come back and do a quarter more. So I can actually lay all the balls out on this thing in about 15 minutes. And I think anyone could possibly do that. So my ultimate goal is to take this whole fear away from them. If, you know, like a senior citizen, old fucking man can actually do it, you guys can do it, you know. So it's not that hard. It's fairly simple. So I'm actually going to pass these chips out so you can actually see the chips. And I have this lens right here so you can look at it. The light does work sometimes. You press hard on it. Sometimes it doesn't. Neither one of these chips are any good, so you're not going to hurt them.
Yeah, just one.
Yeah, take both of them. One of them's been bald. The other one hasn't been bald. There you go. Kind of pass that around. So yeah, so just recently I was talking about why I like to speak, and it dawned on me why I like to speak. It's like being in second grade. It's like a show and tell. You know, it's like fun. I remember that's where I got addicted. I realized it was second grade. When I could bring cool stuff and show people and take the mystery away from stuff so everyone has some fun with it and actually learn something. So, and that's why we did it. So the next phase is, once you get that done, you take that and you put it in an oven. Let's get it right. You put it in an oven, okay? So I have a little silicone pad that I put the chips on, put it in an oven, and the oven was originally set at 250 degrees Celsius when I did the entire board. So I thought, okay, that seems to be a good reflow temperature. It seems to be the recommended. Yeah, it is the recommended for boards. It's not the recommended for chips. It turns out, like I said, solder melts at 180 degrees Celsius. So to actually get a good reflow, you need to come up to about 205. Once you hit 215, there's an interesting thing that takes place. It's called burning. So if you take a look at this chip, see that? And you go, that's after. Let's get it right here. Come on, it isn't going to do it. Damn it. Oh, now it's going to do it all of them at one time. Okay, hold on a second. See how green that one is? See how brown that one is? That's an indication that something did not go right. So then I go back to the drawing board, okay? I'm like, what should the temperature be? So then I found out, I think the temperature was at 215 or 220 degrees. The fiberglass substrate of chips will start to physically break down, okay? So 250 degrees is like 30 degrees above failure, okay? Which turned out to be this case. So I initially went ahead and put the chip on the board and nothing really happened. You turned the power on, it just sat there. So I pulled the chip back off, cleaned it off, put it in a chip reader, it was dead, freaking dead completely. Nothing was gonna work on the actual chip. Burn it to a crisp. So the next thing was, like I said, figure out the temperature, did some research, reballed a chip, and that's where the second one I reballed. Remember, this is like the first time I did this ever. Reballed the chip, put it in the oven, pulled it out, and that was the 122 balls with all the blobs. Failure, flux was bad. Go back to the drawing board, clean the chip off again, reball the chip. This is all in one afternoon. Reball the chip, and I'm thinking, how many times can I cook this until it goes away? Which was my fear. So those two chips there, one of them was overcooked because I did a bunch of experiments with it on reballing and eventually killed it too. But go ahead and set a new temperature, because this particular oven lets you set 2 of your own temperatures. So you set a good temperature curve, and I brought it up to about 200 and I think it was 205, 206 degrees Celsius. And the chips that I'm passing around, you'll see one of them that's been reballed. The balls are on that, so if you have a little microscope, you can look at it and see, or the little lens, look at it, see the little chips on, or balls on it, you'll see how they're done. So another example thing you want to look at here, you got to see this. Which one's this? It's 30 balls, 30 millimeters. Okay, so in the case with this thing, the pads on the chip were actually 30 millimeters width. You can get that data from the data sheet. So you find a data sheet, and you can go ahead and figure out what size of balls to use. They vary in size. The most smallest ones, which you see on these ones, are the 0.25 millimeters or 0.3. I actually reballed that one there with 0.3 millimeters. The pads were 0.3. The screen that I had was 0.25. So, and I didn't like the screen because if the balls weren't perfectly round, they wouldn't go through the holes right. They'd clog it up. There's all kinds of issues. So I'm going to pass these around so you can get an idea. Now I've used some of these, but when you look at this and you look at the bottle and you see that it says there's 25,000 balls in this bottle, okay? I've probably used 10,000 of them. Now only about 400 of them actually ended up on stuff. The other 7,500 of them are in my room somewhere. I'm not quite sure. I actually told my wife, do not let the dog in here. I don't know how much lead poisoning you could get from that, but I don't want my dog wandering around the room and tracking these microscopic balls all over the place. So here you can look at it. So if you open it up and you spill any, I expect you to put them back in and count them for me. So if you could actually pull that off. So we get to that point, and now we've got it reballed. We need to put it back on the board. And this was kind of fun. It was like, okay, we got to put it back on this board. How are we going to go about doing that? So both of these boards have been butchered, which is not a problem. So what we did is you take the pad where the chip came off, and there's a line that goes around it, and there's an indicator where pin 1 should be to line up. It's fairly easy to do. You clean the board, you flex the board the same way you did the chip originally. You line it up. I did it under a microscope just to make sure I had even edges all the way around. You put it in the oven. You crank the oven up, and the one I use brings it up to about 245, 250 Celsius, and you let it run through. But before you put a whole board in the oven, you got to take a couple things into consideration. And what that is shit melts, okay? So you got to think about that. So I did. I actually thought about that one before I started down the path. So I figured, okay, I got to figure out what melts so that when I do my good board, I don't damage it. So remember, I already burnt one chip, so I got a board that's no good. So I actually fed it into the oven at 250 degrees Celsius. And if you take a quick look at and pass that around, you can see the components that melted. That was my test sample. So then I take my good board and I remove the components that melt. In this case, it happened to be the speaker and the 5-volt jack. The rest of them, because they have these big metal shields around them, held up to the temperature pretty good. So they didn't melt or disform or any of that type of stuff. So we're able to actually get it all reflowed. So we put it through, we reflowed it, brought it back out. I let the board cool down to room temperature. I soldered the components back on it to keep them from melted, to get it back to normal. And then I decided, let's put power to it. So I hooked everything up. I powered it up on the UART bus, and I see it starts booting up. And then I see it go to hell in a handbasket. Stuff starts failing. There's memory errors. There's all these freaking errors. It's kind of what happens when, a Linux operating system isn't quite meshing because files are messed up or whatever. And I'm not sure how, but after the thing booted up, I didn't hook the Ethernet to it, and I let it go through a reboot cycle. So this thing phones home. So if it doesn't phone home, it reboots. It keeps rebooting until it connects to the cloud service. So I sat there and I let it reboot 3 times. On the 3rd time, it fixed all the bad memory locations on the chip, lined everything back up, and it came up working. So which was cool. And that way, I could actually tell people I successfully did this instead of wasted $300 worth of equipment. Yeah, I have like a whole bunch of these. Matter of fact, literally the 2 days before coming here, I was doing some work, and the chip that I was using for the presentation, I was going to plug into the device so we could show you the file system mounted up, had balls on it, and they can't put them on the readers when there's balls on it. So I removed the balls, and somehow I damaged the chip and it's dead. I'm like, well, there's like my freaking presentation. So I'm like, oh shit, I got to go to the store. So I drive back to the store, one of the local hardware store type things that had this technology. And I go in there, and you know what? They're like on sale. They're normally like $70. They're like 38. I'm like, I want two. So I got one at home and hasn't been damaged. So now I have a whole stack of these, which is starting to add up to some serious money. But if you've ever been in my lab and seen all of the butchered hardware laying around, yeah, money's money. So that from that standpoint, there's only one thing left to do. Let's see if we can actually do that. So here we are. Let's clear the data. Let's reboot it up. And this is the actual device that I originally did this whole attack on with the goal of getting root access. Now, I've not done a firmware patch or upgrade on this thing. I'm thinking that's the last thing to do after all this work. I'm going to do a firmware upgrade on this thing from the manufacturer and like overwrite all my stuff. So we go ahead and we go Bubba. Come over here. Hold on. Should have waited for that to come up. Okay. So the account I created was Bubba. That didn't show up. Something ain't right. Hold on. Need to learn how to type. Okay. There we are. We logged on. SU. Test 1, 2, 3, 4. And now we're root. So we're able to gain root access to the device, which was like cool. So after this whole project, I have another project I want to do, and it's basically meant to just be freaking scary. But what I want to do is I want to go out and buy like 3 or 4 different products like this, different manufacturers that are using like embedded multimedia controllers, and I'm actually going to rewrite all of them so that when you plug them in to use, they phone home with an SSH reverse shell to some location, just to create a device that can actually do that from kind of a proof of concept. So you start thinking about what if somebody wanted to contaminate some of the supply chain? How easy would it be to go to the store and buy one of these things? Often they're not shrink wrap. They usually just have a little plastic seal. Go to the store, buy something like this, alter it, which is easy to do. If I could do it, anyone could do it. And just return it to the store. It's going to go back on the shelf. I mean, think about this. How many times you've been in the store and bought a product and the seal was broke? So think about that if you go to the store and you're going to buy something that's IoT-based or technology-based and the seal's broke on the package. You know, now that's easy enough to hide, okay? I won't buy a package like that. I go to the store and the seal's broke. I'm like, I ain't plugging that into my house. I don't know what's been altered. I know what I can do, and I know I'm not the only one that can do that stuff out there. Right now we have another 200 people that can do that stuff out there. It's not that difficult. Just needs a little bit of patience, a little bit of equipment, a desire to actually learn how to do some of this stuff. And it's not hard to figure out. This is kind of one of the things I do at Rapid7 as part of my role is kind of research technology like this. And I often develop methods like this, to try to learn methods like this to retrain other guys that do assessments and testing. Because they may not encounter, like the embedded multimedia controllers. They aren't always that common when it comes to IoT technology. So when the first time I come across one, I went and did all the research and go, well, what is an embedded multimedia controller? How do I leverage it? How do I gain access to it? How do I alter the data? How do I manipulate it or do something with it? And then I take all that knowledge, the tools, the methods, methodologies, and I use it to train other people. And of course, come here and hopefully show you guys some stuff. So, any questions? Yes, sir.
So if you're good, you can maybe do this once, twice on a board before you're hooking all of them
I think if you're cautious with temperature-wise and do some experimenting, I'd never buy one board and assume you're being successful the first time. I have like 5 now, okay? But it was multiple different tests and multiple different things I can do. I think you could probably, where I screwed up on that one board the other day, the other chip, was I wasn't paying attention. I was like daydreaming, and I had an 850 degree soldering iron sitting on the top of it while I was like lollygagging out the window. Okay, so it was just something stupid I did. And when I noticed it, I was like, oh crap. And I'm thinking, I wonder if I damaged this chip. And the answer to that, yes. So I think if you think about the temperatures, you follow the processes, you don't shock the device, you bring temperatures up slowly. Like when you go to clean the device, I use, I don't know if anyone's familiar with ChipQuick. ChipQuick makes a kit called an SMD removal kit. It's a very low temperature solder. It's good for removing component level devices because you melt this big blobby solder on there. But they give you this flux. I love the flux. It's the greatest flux in the world. Flux is your best friend. Just pour the flux on there. So if you get ready to clean the chip, you just soak it down with the flux. And then you take a really small solder braid, not big, wide solder braid. That absorbs too much heat. Very narrow solder braid. And just drag it across the device quickly. You'll never overheat the chip or damage it. And it'll clean it up good. Alcohol swab, everything's off of it. If you do the oven, make sure your temperatures are correct. You get a good sweep up. And there's probably even science out there specifically on how some of these settings should be done. There's a lot of documentation out there. So consider that when you're doing the chips. And you're dealing bigger chips or smaller chips, you need to take all these different variations into place. But I think you could probably take the chip off and do this probably a half dozen times or more if you do it right before you kill it. Any other questions? Yes, sir.
What is that device?
Oh, the brand?
No, what does it do?
Oh, this is an IoT hub. It's used for controlling like lights, security systems, garage door openers, all that type of stuff in a house. Any other questions? Yes, sir.
Could you install a backdoor for updating the firmware on the MFC?
Yeah, you could. So as, like what you're saying, in this case here, we modified the firmware by pulling the device off of it, exploding out the firmware. Every embedded device, and I've not looked at all of them, but every IoT embedded device that I've had a UART console onto the device, no matter how I did it, always had DD installed. So that gives me the ability to alter the chips right on there, because that's how they do the firmware upgrades on these devices. It's typically going to be 2 partitions. So everything you see me do to the chip on my Linux system, you can do to the chip actually on the board live, once you get the root console on the device. Another example to gain that level of access, and maybe we'll do another talk next year on it, is actually breaking out of like U-boot. And a number of you have probably seen that. So you can do like pin glitching. So during the boot process, you kill the main processors, or not the main processor, but the main chip's data line by taking it to ground after U-boot started up. U-boot can't load the kernel, so it drops into basically a console mode. And at that point, you could alter things like which partition's primary on the root file system. You could actually set boot arguments to force the device into single user mode. Single user mode is going to give you root level access at this level via the UART, and at that point you can alter any of the code on the device. It's a method I'll often use for getting firmware off a device. If I can glitch the device or glitch the chips that cause it to go into U-boot mode, I'll actually put it in the single user mode, and at single user mode I can do a lot of things. I can bring up the everything from the network connectivity, enable the USBs on the device, and then I just DD all the data off if I need to, onto a USB that's connected to the device or into the temp folder, and then TFTP or SSH it off the device once I brought up the network, alter it, and then bring it back on the device and use the device's DD to rewrite it back to memory. So there's a number of things you can do to easily alter these devices' configurations. This was the Ginsu chef style. Okay, the brutal. Yes, sir.
If I were to start doing this, is there any specific device you'd recommend, like big friendly that can go as EMC UART?
Yeah, yeah. With the eMMCs, most of the time you're going to run in those two I talked about, the 153 and the 221 ball devices. So you don't need to buy the entire set or the more expensive ones, or you may be able to go to find resources online to build your own devices if you're into that. Then the next thing is, how do I get the device off, the chip off, and put it back on safely? I would recommend getting an oven or one of the stand-up IR stations. They're more expensive. The ovens are less than $200, and it'll do most of your average boards that you're running into. And with those two things, you can pull the chip off, you can read it. If you can read it, you can pull it off, alter it, put it back on, and then reballing it. And in the cases of reballing it, it comes down to how well your eyesight is. I like the reball jig, that blue reball jig, purely for just holding the chip. I don't use the screens, and that way I can redo it. And then finding some level of microscope. There's a number of devices out there. Like I said, I would recommend the amp scope, but it's a little more pricey. So, you know, what is the overall price point for doing some of this stuff? I'm probably not the best person for measuring that, because if I'm sitting there and I'm like, oh shit, I need this, I just buy it for being able to do that. But if you want to go the cheap route, I think you could really, if you can find yourself a budget of $500 somewhere, you can start building a really good kit for doing some of this type of stuff. Like I said, the microscope is $185. The oven, you can build your own oven. You can go buy a junk toaster oven and build one from that. I've known people doing that. So you can build some of the stuff yourself, and you pick up a lot of the pieces and components you need fairly cheap.
Like any specific IoT device, this mainly does that. Sorry. So like if I wanted to start, is there an IoT device?
Oh gosh, the thing is when you want to start, you want to find some of the cheap stuff. So often if you go buy some of the really cheap camera systems that are like $20, $30 off Amazon, you'll find that they may not have embedded multimedia controllers, they may have other type of memory storage on those, but often I find you are wide open for root access on those devices. Probably the last 4 that I popped open on the cheap cameras, you just look down there, half the time they mark the board with where the UART's in. You just put a header on it, plug into it, and you're root, man, and you can start rewriting the stuff. So I think we're out of time. Thank you very much. Hope you enjoyed it.